Hi there. As promised, we're going to work on determining reaction order given some data. Um, the standard way of doing this by brute force, by just plotting your data various ways to see if it's linear, just just kind of time consuming. And what we want is a method where we can just do one plot and the plot tells us the order directly. So that's what we're going to do. The first thing we want to do is we want to get our data and we just want to plot our data. So let's do that. I have uh, data from Levine. This data is from Levine exercise on page 528. It's arsenic acid decomposition data. And it starts out with 100 millimoles, so it's pretty convenient. At time zero, you can see that data here. So let's, first of all, just read this into Grace and see how it looks. Okay. Looks exponential or logarithmic. It's hard to tell at this point. That's kind of the whole point, right? So remember, the first thing we want to do is get rid of the connected line. And I like circles, so I'm going to make some circles with some filled symbols so we can see them. So there's our data. And of course, let's save this. Okay. So what we want to do is in Levine, um, Levine suggests that you, if you're, for example, determining half-lives or fractional lives, Levine suggests that you just read the different points off your plot. That's difficult or problematic for two reasons. The first reason is, well, we don't have a line, right? The data that Levine showed in his example didn't show the data points, it's just a line. So you could read off that plot a little bit easier. But we don't have a line. The second problem I have with that is it introduces a lot of uncertainty and error. And if we really want to do this as precisely as possible, we should give ourselves the best chance possible to get some good data. So what I suggest doing is creating a regression line. And so let's do that now. Remember that Grace has a number of canned or predetermined regression. This is really not, that's why it says regression, not linear regression, but these are all kind of canned. And you might think, okay, this looks kind of exponential at first. So let's try an exponential fit to this data. In other words, a negative exponential. We're going to want to load the function. We're going to want to start it at 0, and we'll end it at 300. In other words, where our plot goes. And let's just do 100 points and see how this looks. Okay, so there's our equation, a negative exponential, as I said. And Now, if we look at this data, it's not really very good fit, right? It misses both at the low end and the high end, and it's just not very good. So let's try something else. Let's try an inverse fit. Notice that Grace's inverse fit includes a constant, so it's 1 over a constant plus bx. That's a little different than a straight inverse fit, but that's what we're going to try. And we'll leave the same parameters here and see how that looks. Okay, this looks better to me, right? So let's use this inverse fit function to determine our points off the line, right? So let's clean this up a little bit. Let's get rid of that first line. And let's make our second line a little bit more distinctive, right? Okay, so there's our line. So what we should do is you go to the console and take note of the function and write it down on your piece of paper, and then we'll work from there. So the idea here again is that we can use this data. What we're going to do first is we're going to do a fractional life method. I'm not going to use half-life. I'm going to do something a little different just to show you how that works. And we can also use this data separately in a Powell plot. So we will do both things, but first I want to discuss the nature of these two plots on the iPad. Okay, so let's discuss the couple different ways that we can get a better way to determine reaction order. The first way is fractional life. This is described in Levine at first as a half-life method, but it doesn't have to be half-life. It can be any fraction, because what we're going to do is we're going to define this fraction alpha as a over a naught. This is the typical representation of fraction that we have, right? So when we have this, what happens is the order equations, let's call them the order equations, that we have become alpha to the 1 minus n equals 1 plus a naught n minus 1 times n minus 1 times the rate constant times the time to get to that fraction. Okay, so this T alpha is the time it takes to get to that particular fraction. We can solve for this fractional time. T alpha equals alpha to the 1 minus n minus 1 over a naught to the n minus 1 times n minus 1 rate constant. All right, so we can linearize this. A log or an ln, doesn't matter. I'm kind of partial to natural log, so I'm going to use a natural log, but it doesn't matter if you use a log base 10 or a natural logarithm. So you get log of T alpha equals log of this other stuff. Let's put this in square brackets. This is essentially going to be the constant factor on our plot. And then we have the log of each starting concentration, right? So the slope equals minus n minus 1. In other words, it's 1 minus n, right? So that's pretty handy. Okay, so let's think about how we have to do this, because it's a little bit tricky. Okay, if we start with some data, let's say that we have some concentration data versus time, right? let's say that we start off with 100% or 100 millimolar, or whatever it is, at time 0. All right, so if we decide that we want our alpha to be 0.75%, this is the number Levine uses. I'll come back to this in a second, why we might want to choose 75% left. In other words, 25% of it's been lost. Then we can either measure this in our experiment or read it off our plot. I think Levine reads it off the plot. But what we're going to do is we're going to use our equation of our line. So what we want to do here is we want to find the time it takes to go to 75 millimolar or whatever it is. And then this is going to be the T alpha equals 0.75, right? So in other words, the A naught for this pair is 100, and the T alpha would be whatever we measure for that time going to 275. The problem we have, well, first of all, the good thing is each new data point may serve as a initial concentration, or we can read this off the regression line, which is what we're going to do, but same thing. However, when we do this, each T corresponding to this now A of T, which we're going to set equal to an initial concentration, this T is not 0 like it is in our first point of 100. So what we have to do is we must subtract off the time when our A naught occurred. Right? If we make a cartoon of a plot, we can kind of see why this is, right? So here's my curve, right? And what I'm going to do is I'm going to use this as my A naught. And let's say this is a time of 5 minutes. Okay. Well, what I want to do is I want to measure the time where we're going to be, say, 3/4 of A naught. In other words, so this time increment here is going to be T 0.75. Right? So let's say whatever this is T. Let's just say this is T. You can see that the 3/4 time, T 0.75, is going to be T minus 5 using this picture, right? So every time we set up a new point as a new starting point, we have to subtract off the time that corresponds to that data point. So this complicates things a little bit. We have to be aware of it. If you look at Levine's exercise or example 16.2, you can see how he does this. He has to subtract the times off. And if you're not careful about this, then you're going to run into problems. All right. So from our plot, what we found was the equation of the line, y equals 0.00964 plus 1.3647 times 10 to the minus 4 times t to the minus 1, right? Remember, it's an inverse plot. All right, so let's solve for our time because this is going to be useful for us. The time is going to be 1 over our concentration minus 0.00964 divided by 1.3647 times 10 to the minus 4. And this is going to give our time in minutes. This is very specific to our plot. Okay. So perhaps the easiest way to do this, at least for most of you, you could set up this calculation. You could generate the data in Grace, because Grace does function as a spreadsheet program also. But maybe the easiest thing for you to do is to create data in a spreadsheet and then re-import into Grace. I think conceptually that's the simplest thing to do. So let's see how that works. And here's my spreadsheet. What I've done now is I've created a column of A naught times, initial concentration starting at 100, and I've just gone down by 10 units every time. What this column is, all this column is 3/4 of the previous column. So this is setting up my 3/4 time. And then what I have over here is I have the representation of our equation over here on the left in order to find that 3/4 time. Now notice that really what we have to do, if we look at the second point, you can see that I've done a subtraction, right? I've taken the time to get to 90, and I've subtracted the time to get to that 3/4 point of 90, 67.5, minus the time found at 90, right? So this is the time increment I talked about before. This doesn't work super well for the very first point. You'll notice that the times are the same to within error. So actually what we probably want to do is not use that point, just because it's going to throw off the rest of these points, which work very well. Now you'll notice that the 3/4 time increases as we go on. In other words, it's inversely proportional to the initial concentration. This means it's not first order, right? Could be fractional order, could be second order, but we don't really know the order. Okay. All right. Okay, here we are back at the computer, and here you can see I have the data from the spreadsheet that we just created open. So what I'm going to do, the first thing I'm going to do is I'm going to get rid of this first point. Okay, and what we're going to do now, this is our original plot, right? And what we've really done is we've created 3/4 times, or we've read 3/4 times from this plot effectively by using that equation of the line from the spreadsheet. So there's the data. So now what we're going to do is we're going to create a new plot. Let me save this. Okay, and we're going to read in our data. Now recall, and I'll put this up on the screen so you can see the equation on the iPad. Recall that what we're going to do is we're going to plot the log of the time versus the log of the initial concentration. So in other words, we're going to swap these columns, but that's not going to be hard to do in Grace. So the first thing we'll do is read in this data. I have my data file set named a little improperly because I decided to go with 3/4 time. Okay, so there's the data. the first thing we're going to do is we're going to turn it off because we're not actually going to plot this data itself, right? We're going to take the logarithm. So let's go to transformations and evaluate expression, highlight our data set. So remember, the first column, which Grace now considers to be the X column, is our initial concentration. And the second column is the Y, right? And since we just have one data set we're referring to, we don't have to do anything but say Y and X, right? So I can say X equals log 10 of X, semicolon, Y equals log 10 of Y. Now, as I said, I'm partial myself to natural log, but I'm going to use the log base 10 because that's what Levine uses, and you'll be able to compare the data better. So we hit apply or accept, make that window go away. Now, of course, the data doesn't show up because the limits on our plot are based on the initial data. So let's look at our data to see how we want to change our axes limits, right? So our data goes from about 1.3 to 1.9 on the X. So let's change our X from 1 to 2. That Siri button is really close to the delete key. It's very inconvenient. Okay. And let's use spots of 2/10. Now you can see our data way down here at the bottom, right? And the Y goes from about 1.4 to a little more than 2. So again, let's go from 1 to 3. And we just pick appropriate tick marks. Okay, so there's our data. That looks really linear. That's nice. So let's go ahead now and write in what we have. The y-axis is going to be log of variable t and then we have to change back. And then what I want is the symbol font, F, S, Y, M, B, O, L. And I'm just going to use the symbol font to use T alpha, right? And maybe we put in 0.75, but let's just use T alpha. But I need to make sure this is a subscript. It's really hard for me to see this. Okay, I think that's good. There we go. Okay, and the x-axis is the log base 10 of a 0. Okay, so let's do what we do to the sets. Remember, we're going to turn off our line. We're going to turn on our symbols. We're going to make our symbols look nice. Okay, that looks pretty good, very linear, right? So we should get a good result here. So let's go to regression. Now select our set. This time we're going to do a linear regression. We're going to load the function between 1 and 2 because those are the limits of our plot. And for a line we just need 2 points. console says that, let me get it here, y equals 3.38 minus 1.0006. Okay, so let's write that down on the iPad. Again, if you were going to present this for an assignment or a paper or something, we would probably want to make sure that this looks nice, and we would want to save it. Okay, so let's go back to the iPad for a second and see what our answer is. All right, we're back. So if you recall, from the plot, the equation was y equals 3.3888 minus 1.0006x. Now, if we compare this with our equation that's up here, right? We could just go ahead and copy this. Okay, we can see that the slope is 1 minus n, so we can say minus 1.0006 equals 1 minus n. In other words, n equals 2.006, right? But second order, this worked out really well. We got a really good determination of a second order fit. That's very nice. This is actually mathematically very similar to the fractional life method, but it's more of a graphical way of doing it. And if you read the discussion in Levine about what he says to do, is he basically says to make your calibration Powell plot, which is figure 16.6 in Levine, and then plot your data on the same scale on some onion paper or something, and then slide it around until you can match the curves. So the idea here is each order gives a different, unique, well, I guess that's redundant, huh? Curve, and we will plot our data, match it to a Powell calibration curve. Let's look and see how Powell plot works. We define the alpha exactly the same way as we have before, A over A naught, but we also have this other parameter phi, which is the rate constant, times the initial concentration, the n minus 1, times time. Okay, so what we're going to do here is we have this expression, a to the 1 minus n equals, a to the 1 minus n minus 1 equals n minus 1 times this phi parameter. If you compare this to the fractional life expression, you can see that they're really the same thing. So what we're going to do is we're going to plot log of the alpha, which gives us minus phi, right? So what do? We really plot the alpha versus log of the phi, in other words, versus ln of t, right? Here's the t. Here's the t. So it turns out that if we plot the alpha versus log of our time, then we're going to get the same curve to within a constant. So the difference between log of t and log of phi is log of Ka to the alpha naught to the n minus 1. This is a constant. So what this is going to do is we're going to move our data back and forth along the Powell plot in order to match it up. Okay, so we're back at the computer. Let's see how to treat our data with a Powell plot. What we want now with the Powell plot is the original data. And the nice thing about this data from the Levine example is this can be considered, or this can be turned into fractional data very easily, right? And I mean, it's just math either way, but conceptually it's easy because it's starts at 100 millimolar. So remember, what we're going to do is we're going to plot the alpha versus the log of the time. So we can use this data. We're just going to create a new plot, right? Actually, we're going to use the Powell calibration plot. This is saved for you in the files on Canvas, and this is what it looks like, right? So you have to be careful when you read in the data that you do not have it auto scale the axes, because it'll totally mess up your plot, right? So in other words, we're going to import the data. Make sure I know what the data is called. Here's the data. And here's the auto scale, right? So I want to make sure and turn this off to none. And hit accept or OK. Now, here's all the data sets in the Powell plot, but here's our new data, right? Just as we expected. So let's now manipulate our data, highlight our last set, erase what we did before. So now we want to plot the alpha as the y and the log of the x, right? So we're going to say x equals log 10 of x, semicolon, y equals y divided by 100, right? Okay, so let's hit accept. And this should create a new data set. There it is. Let's look and see what this looks like. That looks pretty good. Now, the first point's minus infinity. Infinities don't really cause Grace problems. Division by 0 does, but that's okay. It's basically not going to give us this point, but that's okay. So notice the y values, right, are between 1 and 0. And what we want to do is we want to find about the midpoint, right? In other words, we want our midpoint of about 0.5. The 0.5 point on all these Powell curves is between, let's say, -5 and 5 units. Well, in our data, the midpoint is at about 1.7 to 2, and we want to put that pretty close to 0, right? So this is the x value that we want to scale our data by. We want to shift it to the left a little bit. We want to shift it to the left. I'm probably doing that backwards on the video, but you get the idea. All right. So let me close this window and leave this one open so we can see. We're going to do another transform. We're going to evaluate the expression. This time, all we're going to say is that x equals x minus, and I'm just going to guess 2. Now, you can see the data here. It's really, Grace chose a really bad color for the data. So what I'm going to do is I'm going to turn off this other data just in case it ever shows up. I think it's going to be off the scale all the time. cyan. It picks cyan. Let's pick black, right? And let's make it a dashed line so we can see this. And let's make it a little bit thicker so we can see it. So there's our data. I hope you can see it, this black line. Now, what we can definitely tell is it doesn't match the blue line very well, right? It crosses over the blue line right here. So it doesn't match the blue line. The blue line is 3/2 order, so it's definitely not 3/2 order. Let's now create another data set that all it does is shift the data a little bit back to the right. So we want to compare it with this pink line, which is second order, and the kind of orange line, which is third order. Let's try to put it right in between. So we have this value. Let's try to find a value that's right on the line. I don't know, we want to move it about 0.2 units back to the right. So let's do another transform, evaluate expression, x equals x plus 0.2. And we want to make sure and pick our last chosen data. All right, so there it is, right? Here's our new data set. Let's make this black also and dotted so we know it's the same data, right? So what do you think? Well, I don't think it matches the n equals 3 line very well at all either, but it looks pretty good for that magenta or pink line, which is n equals 2. Now, this should not be surprising, of course, because we already plotted this with the fractional life method, and we found out that it was second order. So we should get the same answer here too, right? It should match second order here. And this is how you do it. You just put your data, plot your data, right? Which is going to end up being not in the right place as the Powell plot. And we just shift it left and right and compare it to these different lines. And that tells you the order. So this data is second order. We've confirmed it through a Powell plot, and we've confirmed it both through a fractional life method. The next thing we're going to work on is some data that doesn't really give you a good answer if you brute force it, right? So this particular data, if you had plotted brute force, you would have figured out pretty quickly it was second order through an inverse plot. And actually, if you think about it, the fact that the data fit an inverse plot best fit line strongly suggests that it's second order, right? But that's not always the case. And so the next thing we're going to look at is a data set that you must use one of these methods, or else you don't get a very good answer at all. Okay, so as promised, let's look at the Levine problem 1630. This problem gives you a set of data, and it asks you to plot it as if it was first order, in other words, log of the concentration versus time, and second order, 1 over the concentration versus time, and see if you can figure out which one's linear. So let's do that. We'll do that including the regression coefficient, see if that can tell us anything. And then in the end, what we'll do is we'll do a Powell plot. I think Powell plot's easier. If you do and I'll mention this later too when we do it, but if you do a fractional life plot, you actually have to do 2 plots, right? You have to plot your data, and then you have to get the curve from the data, whether you do a regression or eyeball it. Then you have to generate the fractional life data and read that in and plot that. And the nice thing about the fractional life is the slope of the line, the regression line you get from the second plot, is 1 minus n, right? So you get the order pretty clearly. For a Powell plot, you read the data into the plot and move things around. So you only have to make one plot, but you do have to move things around. So it's up to you which one you think is easier. They're both about equally effective, and they both provide a clear way to tell you the order, as we'll see. Okay, so what I have here is I just have two plots set up, and you can see I've already labeled one of them to be logarithm of the concentration, the other one to be 1 over the concentration. I'm going to read the data into these plots and then do that manipulation. Okay, I'll just do that really quickly, and I'll come back and show you how it looks. Okay, I'm back. Here we can see the data. I've plotted the points. And before I do a regression, if I really had to give you an answer, I'd say it looks like second order to me. It looks like there's a little bit of a bump in the logarithm data, but you can never trust your own eyes. You have to do this appropriately, and you have to apply the math to the method to get the answer, to get the best answer. Okay, so let's do our regression. I'll do the top one first. This is going to be pretty straightforward, right? We have to make sure we select the correct data set, correct plot. I'm going to do the top one first. Linear fit, I want to plot the function. I'm going to start at 0, and I'm going to stop at 25, and I just want 2 points. Okay, that looks pretty good. I'm going to look at the information for the plots after I do both of them. Click on the second plot, click on the data set. Everything here should be set up good enough for the plot. Do that one. So now I have 2 lines, and I don't know, now the logarithmic one, the first order one, looks a little bit straighter to me. Okay, I'm just going to now go in here and put in my lines. I'm going to make it look nice. I always send the regression line to the back so the symbols sit on top of it, if that makes sense. Just looks a little nicer to me. I'll do the same thing with this one. Send this to the back so it sits behind. Okay. So there are our 2 plots. And what we want to do now is we want to open up the console and look at the information from the plots. Of course, if you were doing this for real, you would probably want some information from the equation of the line, but here we're trying to check the order, right? And that the type of plot is supposed to tell us the order. All right, so for the second plot, the 1 over A, the second order plot, the coefficient is 0.99855. I'm going to write that down. And I'll put it up on the screen here so we can look at both of them. The logarithmic plot, the top plot, of course it's negative because it's a negative slope, is 0.9999. There's 4 9s, and then there's a 4. Okay, so probably someone told you with regression coefficients, the more 9s, the better. So this looks like first order is the better choice, but they both look pretty good. They both look pretty linear. And I would say that if you presented both of these plots, they're not conclusive, right? All right. So what we're going to do next is we're going to enter the information into a Powell plot. So let me open up the Powell plot. Here's the Powell calibration curve. So what we're going to do is we're going to load our data into this. Now remember, a Powell plot, all you have to do is plot the fractional amount at each time versus the log base 10 of that time. So you do have to do a transformation, but it's pretty simple. So I'm going to go ahead and do that here. Now here's the data. That's not it. Here's the data. And you can see that it's the time in minutes is the X, and the Y is not fractional, but all we have to do is divide all the points by the first to convert into fractional. So let's go ahead and do that. All right, remember we want to make sure that auto scale on read is on off or none. And what's going to happen here is we're not going to be able to see the data because it's not appropriately scaled. So let's do our transformation. There's a lot of data already in the Powell plot, so let's make sure we click the last one. All we have to do here is say y equals y over the initial y value, which is 6.35. You can see that right here, 6.35, semicolon, x equals log 10 of x. Now, I know I've said before that I'm partial to natural logs, and if we're just linearizing something logarithmically, I like to use natural log. But this particular Powell plot was set up with log base 10, as you can see on the axis here. So that means that when we manipulate this data, when we transform this data, we have to make sure and use log base 10, or the curve is not going to be correct. That's very important to realize. All right, so I'm going to apply this, and I'm going to leave this window open because I'm going to use it. Now here's our data, right? Here's our data. It's behind the legend, but I want you to notice one thing, is that the data is contained all in this area. So when we slide it over to the left, right, when we slide it over to the left, it's going to stay in this area. So what I want to do is I want to look at just that area, the area from 0.6 to 1 on the y, and from -1 to 0 on the x, because all the rest of that area of the Powell plot is not going to be useful for the comparison. So let me do that now. I'm going to go ahead and scale this. So they're scaling the x. And here's scaling the y. Okay, so this is the area that our data is going to be moved into. Now, let's look at our data. And see how far we're going to have to move it over. So let's just pick a point, 0.7 on the y, which is going to be right here. So we want our data to be in this area here. And this is in the neighborhood of -0.4 in the x. So the 0.7, this 1.25 has to become -0.4. So let's just make it 0.4 by subtracting 1 point, let's see if I can figure this out, we subtract 1.25, 1.65 should do it, right, if I did the math in my head correctly. So let's go back to the evaluate expression. We're going to pick our last data set here, because that's the transform data, and we're going to say x equals x minus 1.6. And let's see what happens. All right, it moved our data over. It's kind of hard to see because it's cyan colored, horrible, horrible color, right? You see cyan. I'm going to make our data black. I'm going to make it thicker, and I'm going to make it dotted, right? All right, there's our data. What's the order? Well, we can compare it directly to the n equals 3 line, and it doesn't match that curvature. We can also compare it to the n equals 2 line, right? Remember, this is one of the two orders we've already plotted. Doesn't seem to fit that very well either. So it's not going to be n equals 3. It's not going to be n equals 2. It's probably going to be, it looks like, n equals 1 or n equals 3 halves. So what we should probably do is try to move it over in between these two, right? So again, let's take the 0.7 point, and let's put it right on 0.4. We missed that a little bit before, and I'm going to move it over maybe about 6 or 7 tenths. You can do this trial or error. 6 or 7 hundredths actually. Right. Again, we have to make sure we select the newly created data set, or else it's only going to move the old data set over a little bit. Now we can see that. We can't see it very well, so let's go to Set, Appearance. Let's make this a big, thick, black dotted line also. All right. So now you have to do some guesswork, right? What do you think? Does this look like the blue line, which is n equals 3/2? I don't think so, especially up here. Up here it coincides with the pink line. Down here it starts approaching the blue line. So since it's meeting the two different order lines in two different areas, it's probably not either of them. I think it's going to be n equals 1, which is this purple line. So what I'm going to do is I'm going to move this data over yet again. Okay, seems like a bit of a hassle, but it's actually pretty easy once you get the hang of it. And I want to compare it to the n equals 2 line. So let me go down here, my new data, I'm going to make it black, I'm going to make it dotted. Now, well, this looks coincident. It's such a good fit to n equals 1 that you can barely see it. It deviates a little bit up here, but all through here, the line's basically coincident with the n equals 1 line. Okay, now if we want to, right, if we want to see this even better, we could find our axes here and we could blow this up even more, right? We could, let's just blow up the y from 0.7 to 0.9. Let's do 0.95 and see what it looks like. Okay, so again, we're looking right here. It looks really good. I think this is n equals 1, first order. Now, if you happen to possess the Levine solutions manual for the problems and look at that, in the solution manual to problem 16.30, it says that it's either first order or 3/2 order according to the Powell plot, but it's probably not, you're probably not able to say which one. I don't really agree with that. I think it's pretty clear it's not 3/2. I think it's first order. Both from the previous plot where we got a pretty good regression coefficient, a little bit better regression coefficient compared to the inverse plot. But to me, the Powell plot is convincing. Now, I also happen to do a fractional life plot. I used 3/4 lives, in other words, t 0.75 to get this, and I got a slope of 1.0006. So again, I'm sorry, the slope wasn't 1.0006. It was, the n was 1.0006 when I did a fractional life plot. That's yet another piece of information that really, really makes it look like first order. So if you were really trying to, if you were doing order for a reaction that hadn't been done before, or a reaction that people were arguing about, then all three of these pieces of information, 4 even if you include the inverse plot, pretty convincing that this particular reaction is first order. Very useful tool. I don't know if you saw the seminar today. Today is November 17th, 2020, in case you're looking at this sometime in the future. Today we had a very nice seminar from an inorganic chemist, and he had a kinetic plot. He was trying to figure out the order of a reaction. He did an inverse concentration plot and concluded that it was second order. And of course, what was I thinking? I was thinking you should do a Powell plot to really determine this, because you might be fooled. But that's just an example. Not that hard to do if you learn how to do it and ever do any kinetics. It's a very useful thing to do. Hope this was useful, and we'll see you real soon.